Okay, so what is a linearization? Let's first find z naught, which is the value of the function at this point, which is f of 0 pi. Okay, so that's e to the 0th minus cosine of y, which is pi, right? And what's cosine of pi? -1. So it's 1 minus -1. Okay, and so that is equal to 2. Any problem with this? No problem here, right? Okay, so then we go to f sub x. Let's try to evaluate this. That's 3 e to the 3x. This is straightforward, and plus 0, of course. Fy, this part goes away, and so negative cosine of y becomes sine of y. You evaluate both of these at pi or 0 pi. So this is 3 times e to the 0th, which is 3. And this one is sine of pi, which is 0. Okay, so the linearization of this, you can write this as f, L of f, or L sub f, or L sub f at 0 pi, or whatever. There are many ways to denote this. Okay, this is equal to, now remember, this is not the function itself anymore. It's a linearization. It's a linear approximation of this function f at 0 pi, and that is equal to, remember, this is fx dx, oh, sorry, I guess I should say z naught first, plus basically dz, the total differential. It's fx dx plus fy dy. And so this is 2 plus 3 times x minus x naught, and then plus fy times y minus y naught, and of course that's 0. So this is 2 plus 3x. That's it. Okay, and usually you will see that the linearization will be a very simple expression, and it has to be, okay, because you can't have x squared or 1 over x or square root of x or anything like that. It's a linear function in x and y, so it could have at most 3 terms: the x term, the y term, and the constant term. All right, so this is it. This is all you do for this. So if you have to approximate, I didn't ask you to do this, but approximate f at let's see, -0.1 comma pi plus 0.1. Okay, so you can see that dx is -0.1 and dy is 0.1, right? All you have to do is just plug this into a linearization formula. Notice here, y doesn't actually matter. Okay, so this is 2 plus 3 x, which is that. And so 2 plus, remember 3x is -0.3. And so it's 1.7, and that is it, okay? If you're, again, interested in the actual value, you can do so. You can calculate this, and that would be e to the -0.1 times 3 minus cosine of pi plus 0.1. Okay, and you can calculate this. I will take my calculator out and figure this out, and so it's fairly close to 1.7 as well, 1.7358 and so on. Okay. Yeah, so that's how you can do these problems, and I hope you get that. 2 plus 3x was the linear approximation, and you can do most of the other problems in a very similar way. All right, the last part of this that I have to deal with is called the error approximation or error estimates. Okay, how much can you be off by? Because when you measure actual, in real life, when you measure things, you can be off by some number, right? So the key here is to use the total differential. All right, so what am I talking about? All right, so here, let me give you an example, and I'm not going to give you all the theoretical things. I think you can understand when I start to use the differential. All right, so let's say you have a can, you have a circular cylinder, okay? You have 2 parameters, radius r and then height h, right? You know the volume of a cylinder, pi r square times h, right? Okay, so let's say R is 3. You have the radius, which is 3 inches, and H, the height is 10 inches. Can you find the value of the volume? Ooh, that's not a calculus problem. That's an arithmetic problem, maybe a geometry problem, right? Because, I mean, really, what is this? This is V is equal to pi times 3 square times 10. That's 90 pi, right? What's the problem? And by the way, this is in cubic inches, right? No problem here. Well, that's great in an ideal world, okay? But let's say, I thought this was 3 inches, but it could be off by 0.2 inches. Okay, that's a possibility. And this, by the way, is our differential dr. Okay, and 10, I said 10 inches, but because we are human, it could actually be off by 5 inches. This is our dh. So in that case, how are we gonna figure out what the range is? How much can the volume of 90 pi cubic inches be off by, right? So that's the question that we'll be asking. How much can V be off by? And so this is the total differential, and this is what you will need to calculate. I will give you another example after this, and that's all I'm going to do. The total differential dV is what would estimate, and this is called the error estimate. This is called error estimate, is the partial of V with respect to R times dr plus the partial of V with respect to H times dH. Right? I mean, that's what the differential is. And the total differential actually estimates the error in these situations. All right, so what's the partial of V with respect to R? Okay, that's 2 pi RH. Okay, and then how about VH? If you differentiate this with respect to H, you just get pi R squared, and then you have the H, right? All right, so this is equal to 2 pi RH, and my dr at the maximum was 0.2. Oh, by the way, I should go ahead and start entering the real values in here, because we know what R and H is, right? So once you get this total differential figured out, let's go ahead and plug in numbers. 2 pi. R is 3. H is 10. And dr is plus or minus 2, 0.2. Okay, we don't know if it's plus or minus, okay? But it is maximum plus 0.2, and at minimum it's negative 0.2. That's what it means. Plus pi times 3 squared, that's 9, times dh, which is 0.5 plus or minus 0.5. Okay, now you know that this could be, one could be plus and the other could be minus, right? But this can be written as plus or minus. Now let's multiply everything together. Okay, so you have 60 times 0.2, that's 12 pi. And then you have plus or minus 4.5. 9 times 0.5 is 4.5 pi. All right, now this is a weird expression, right? Then basically you look for the worst case scenario. dV is the error, and dV is not more than, okay, and the worst case scenario is when dV is the maximum, and that can be attained when both are plus and not the mixed thing. So the dV, basically its absolute value of dV is no less than 16.5 pi cubic inches. And so this is the maximum error that we can be off by. We say and we claim that the volume of this cylinder is 90 pi cubic inches. But given these errors, given these sort of error range, then the volume can be different, can be off from 90 pi cubic inches by at most 16.5 pi cubic inches. Actually, this is a pretty large amount of error. Okay, I'll give you one more example, and then I will show you what is called the relative error, and then we'll conclude this section. All right, let's say we have a square box or a rectangular box, okay, and the width is, or length is x, and the width is y, and height is 2. Okay, 2 is just a fixed, let's say these are feet. okay? X feet by Y feet by 2 feet. The volume of this box is 2xy, duh, right? Let's say X is equal to 4 feet, Y is equal to 5 feet. But again, we could have an error of 0.2 feet, and here could be off by 0.1, 0.10, okay? Now notice here, 0.2 is actually 5% of the, my X value, which is supposed to be 4. So this is a 5% error in the X unit, or in the variable X, the length. What I'm saying is we measure the length as 4 feet, but we could be off by 5%. And Y was 5 feet, but we could be off by 0.1 foot, which is 2% error, right? Because 0.1 is exactly 2% of 5. 1% of 5 is 0.5, 0.5, and so on, right? What did I just say? 1% of 5 is 0.05, so 2% is 0.1, okay? So that's that. All right, so now the question is this, right? Again, listen carefully to this practical question. All right, we found the volume of this box, okay? It's 5 by 4 by, sorry, 2 by 4 by 5. And so that's 40, okay? It's 40 cubic feet, okay? That is the capacity or the volume of this box, except the length X could be off by 5% and Y by 2%. Now, these are called relative errors, okay? And relative just means percentages. The question is, how much can V be off by? What percent can V be off by? We say V is 40 cubic feet. Can it be off by 5% or 2% or less or more? Okay, and that is the question. And again, we do our total differential. What is dV? That's V, this time it's Vx dx plus Vy dy. Now Vx, remember this is really easy. Vx is the derivative of V with respect to x, that's 2y, right? Dx, and then the derivative of V with respect to y is 2x dy. And so that translates to, in this case, 2 times 5. I'm going to write something down here, so don't put anything down here. It's 2 times 5 times dx, and dx could be 0.2, right? Plus or minus 0.2, I guess we should say. So you can, just like what we did before, this is plus or minus 0.2. And then plus 2 times x times plus or minus 0.1. Okay, so this becomes like 10, and so this is plus or minus 2, and then this is plus or minus 0.8, and so this is the thing is maximum is 2.8. Okay, so the error that we can get is by maximum 2.8, which is it could be our 40 cubic feet. That is our volume measured or calculated, but we could be off by as much as 2.8 cubic feet. Maybe not very precise, right? Okay, so that's one answer to this question. But I want to come back to this. dV is 2y dx plus 2x dy, right? All right, so what we call the relative error for V is calculated as follows. See, dV itself is not relative, it's an absolute number, like we said, 2.8 cubic feet that can be off by. Relative is the percentage error. So what we do is you divide this by V. Okay, in fact, you divide everything by V. That's going to answer our question, what percent can V be off by, okay? Because dV over V, remember, this is the error divided by V, that would be the percentage of the error, right? And so what is that? Well, dV over V is, and we know the we know the answer to this because this is dy dx. What was v? V, what was v in this? It's a 2xy. Right? And then this goes away. 2 and y go away. 2 and x go away. Right? So guess what this is? This is dx over x plus dy over y. Right? Now, we already knew that this was, what was the percentage on this one? 5% error, right? So this is 0.05. And then dy, see, this is the relative error of x. And this is, of course, a relative error of y, that's 0.02. And so the answer was 7%. So V can be off by 2.8 cubic feet. But remember that 2.8 is exactly 7%. Oh, no, yeah, 7% of 40. So off by 7%. Okay. In this case, it just happened to be the sum of 5% and 2%. Sometimes it's not just the sum of the relative errors. Okay. But that's how you can find the relative error using the total differential and then trying to solve that for dv over v, or in this case, it's in this case dv over v. Typically, it's df, the partial, the total differential df over f. And that will give you the percentage error. That is the maximum error that the value can be off by. Okay, so that's it for section 4.4. I hope you've understood the very fact, and that is the number one takeaway from this section, the fact that linearization is the same as the tangent plane when you are talking about the function of x and y. Right, so if you have to find the linearization, of course, you have the formula, but it is the same formula as the tangent plane formula. Okay, next time we'll be talking about the chain rule, but not the chain rule anymore. We'll be talking about chain rules, okay, because we have more than one. All right, so until that time, I hope you'll have a great week and see you later.